Lesson 5, we'll take a look at inscribed and circumscribed quadrilaterals. So first we're going to start with inscribed polygons. So as you can see below, we have 4 examples of inscribed polygons. What do you think the definition of inscribed polygons are? And if you notice, if a polygon is inscribed, all of the vertices of the polygon are on the circle. So the polygon's inside the circle and the vertices are on the circle. So it's a polygon inside a circle with vertices on the circle. Okay, and we're going to skip over the definition of circumcenter. We won't be using that in this chapter. Let's take a look at circumscribed polygons. So circumscribed polygons is kind of the opposite, right? So in a circumscribed polygon, the polygon is on the outside of the circle, so the circle's inside the polygon. And if you notice, each side of the polygon is tangent to the circle. So let me switch colors here. So the circle is inside the polygon. And then the sides of the polygon are tangent to the circle. Whoops, and it looks like I wanted the definition here, so I'll just draw an arrow. And we've actually looked at circumscribed polygons before. In the previous section, we took a look at the ice cream cone. So if you have an exterior point, a point exterior to a circle, and 2 tangent lines coming off of that point that are tangent to the circle, we have ice cream cones. And we did the walk-around problem, where we have our 3 ice cream cones right here, and we were able to figure out x and the perimeter. So we've already taken a look at these problems. If they're circumscribed, you have a bunch of ice cream cones, and you can use the property of the ice cream cones to figure out different lengths. So we have looked at circumscribed polygons, and again, the definition of incenter we'll kind of gloss over for now. We're not going to use that in this section. So to review, inscribed is when the polygon's on the inside of the circle, and if it's circumscribed, the circle's on the inside, the polygon's on the outside. So we're going to focus today on quadrilaterals that are inside the circle. So we're going to be looking at inscribed quadrilaterals. Again, we have already taken a look at the circumscribed with the ice cream cones, but if it is inscribed, it's inside the circle, and we're going to look at quadrilaterals. Example 1, use what you know about inscribed angles and intercepted arcs to find the measures of the missing angles. So this is a good review of our inscribed angles. I'm just going to pick one of these. I'll just pick the 100, and I'll look at that. It's an inscribed angle that meets this arc over here. And so we know that if it's inscribed and you want the measure of the arc, we're going to go ahead and double it. So if we double that, this is 200. So now I'm going to use the property of a circle. We know that there's 360 degrees in a circle, and I want to figure out, okay, what's the measure of arc DB then? And since we have the 200 for the red arc, if we take 360 minus 200, we'll get 160. And notice that is inscribed. I'm going to erase now and I'm not going to look at anymore. That is inscribed to angle C. Okay, so here's angle C right here. It's the inscribed angle. And now let's go from the arc to the angle. And we know that if we're going from the arc to the angle, we're going to take half of the arc. So angle C is 80 degrees. So I'm going to do the same thing, and I'm going to solve for B. We also could solve for B looking at how many degrees there are in a quadrilateral, but I just want to show you again just to review the inscribed angles. Okay, so now let's take a look at AD and DC, where the 70 degrees is, and we have an inscribed angle, and it meets this arc over here, AC. And using the property of inscribed angles, we can double that to get the measure of the arc, so this is 140. Using properties of a circle, I can figure out the remaining part. 360 minus 140 will give us the remaining arc. What is that? 120. Okay, so this purple part is 120. Did I do that right? 220. Okay, so now that we have that, again, I'm going to erase the stuff we're not looking at. It gets kind of confusing here. And we're going to take a look at the inscribed angle B. Okay, so let's make it green. Okay, so here's B. And the purple arc is inscribed to that. We'll take half, and this will be 110. Okay, so using properties of inscribed angles, we could have also used the property of a quadrilateral, how many degrees there are. We can get all the angles inside the quadrilateral. And now let's take a look at anything that we notice about the opposite angles in a quadrilateral. Okay, so opposite angles in a quadrilateral would be the 70 and the 110. It would be the 80 and the 100. What do you notice about opposite angles in a quadrilateral? Inscribed quadrilateral. So hopefully you notice that those opposite angles are supplementary. Okay, so there it is, kind of our proof by numbers that the opposite angles in, it's called a cyclic quadrilateral, so an inscribed quadrilateral is also called a cyclic quadrilateral. We can see that those angles, opposite angles, are supplementary. So what that means, to generalize, angle A and C, those are opposite. And then angle B and D in this example right here, those would also add to 180, they're supplementary. Okay, so let's use that property then and solve for different angles in cyclic quadrilaterals. Okay, so in the first example, we have parallel lines, and this happens to be a trapezoid. We have one set of parallel lines and two sides that are not parallel. It's an isosceles trapezoid, actually, because these two sides are the same. Okay, so let's solve. We know by this new property that if it's a cyclic quadrilateral, the opposite angles add to 180. So that means that angle D would be 180 minus 120, so that would give us 60 degrees. Since it is an isosceles trapezoid, the base angles are the same, so we have 60 and 60, 120 and 120. So then it says find the measure of BD, arc BD. Okay, so let's find arc BD. It's the minor arc, because it's two letters. Ooh, it's an inscribed angle. Here we go. So there it is, and we have the 60 degrees as the inscribed angle, so the arc is 120. Let's find the measure of the major arc, ADC. Okay, let me find that. A to D to C. Okay, so that's over here. And again, it's inscribed to the 120. So if we double that and get the arc, we get 240. And we talked about how this is an isosceles trapezoid, because you have one set of parallel lines to make the trapezoid, and our base angles are congruent, so it's an isosceles trapezoid. Okay, let's take a look at example 3, find x and y. So if we take a look at this example, we have two letters here. We have x and y. And we know that the opposite angles are congruent, so I'm just going to circle that, or not congruent, they're supplementary. So I'm going to circle the opposite angles. And if you notice, if we use the blue set of angles, y plus x plus 10 equals 180, we can't solve that yet because we have two letters, two variables, and only one equation, so we can't solve that. So let's take a look at the pink, and we see that, oh, x plus 112 equals 180. Okay, so this one we can solve. We can solve the pink one. Let's subtract 112 from each side to get x. What will that give us? It will give us, looks like 68. Okay, so angle x is 68 degrees. And now knowing that, we can go ahead and plug into the blue. We know that this is 68 right here, and we can solve. So I'll do that below. So we would have y plus 78 equals 180. And then to solve for y, we could subtract 78 from each side. And that would give us 102. Okay. So there it is, using properties of a cyclic quadrilateral. The opposite angles of the cyclic quadrilateral are supplementary. You'll be able to solve the problems in the quizzes, assignment 7.5. So if you go to Google Classroom, you can click on the link, and you'll want to finish that for Monday.